going to do one of 4 tests. This next one is going to measure distortion. And so what the audio clip is saying is that, again, it's setting this 1 kilohertz, 1 volt signal. And then on the scope here, you can see it looks really like a perfect sine wave, but there is a little bit of distortion present. And so what the analyzer is going to do now is vary the frequency. Once I click on this little OK button, which meant that I set up the volume control down here to give a 1 volt RMS, which is a 2.8 volt peak-to-peak signal. What it's going to measure now is going to go back down to 20 hertz. You can pick the frequencies you want up to 100 kilohertz and actually measure distortion versus frequency. But the kind of distortion it's measuring is called total harmonic distortion plus noise. And so what it's measuring is the RMS value of everything but the fundamental frequency. So it's going to actually filter out this 1 kilohertz signal when it's doing the 1 kilohertz test, measure all of the components, RMS values, get a number, and divide it by the RMS of the signal that's in 1 kilohertz. It's going to go back and do that at every frequency. What you're going to pick up with this kind of a test is distortion from the power supply rectifier, that green little box I had in the picture before. Because it's a silicon diode, there's very little distortion from that rectification. It's actually smoothed out with those 2 big capacitors. And so the distortion for this amplifier is much lower than the champ because it has a much better rectification scheme. But again, you don't get that sound effect, so you're trading one thing for another. So here's that distortion versus frequency curve. I'll zoom in on it, I think, in the video a little bit. And at 1 kilohertz, it's about 1.5% total harmonic distortion plus noise is what the measurement is. And as I went higher in frequency, there was a little more distortion, about 3%. And as it went down kind of low in frequencies, it started going up too. Part of this up here and up here is that the gain is getting smaller, so the waveform is tinier, and so the distortion gets a little bit exaggerated. So it's really probably not all that bad over here or all that bad maybe over here too, but it's getting worse at the other extremes of sound. But in the audio band, from about 100 hertz to 10 kilohertz, distortion is actually dipping here down to about 1%. So this actually is much lower than any other tube amps that we have. I didn't do it for the other channel, but I actually ran it without the video it. But it was basically the same curve. If they're not, then I know something's wrong with, with something in the building of it or some parts not functioning. Now this instrument we actually have in the lab, it measures what's called total harmonic distortion. It's going to take that 1 kilohertz signal that I had and remove the 1 kilohertz and measure the RMS value of all the distortion components only caused by that waveform. And you can see here that it's a pretty clean looking sine wave, and you got a fundamental at 1 kilohertz, there's a harmonic at 2 kilohertz, and basically 3 kilohertz, and the rest of it's pretty small. And it gives a total harmonic distortion in dB. You got to divide that by 20, make it the power of 10 times 100%, and this turned out to be about 1.57% if I remember right. Very close to what the other analyzer did because the power supply distortion is very low, so it didn't really change it. When I do this for the champ, this distortion is much lower than the total harmonic distortion because I'm throwing out that other part. And then I had another, again, free software package that grabs that instrument. So I was able to print this for Peter, to give him that actually after the meeting. So you can see what the distortion looks like. The other real interesting part is to overdrive this thing. That's what's going to happen next. I'm going to crank it up so it goes peak to peak. And this is why tubes sound different than transistors. So that's coming up in just a second. Well, the load I have right now is not a speaker, but a 10 ohm resistor. And so I can calculate the power that's also going in the load. And with the full signal you'll see coming up here, it's about 17 volts peak to peak. You get about 4 watts. And the power varies with the resistance of the load, or the real part of the load. And then the speaker actually has a variation in resistance, effectively, versus frequency. We call impedance. Now I overdrove it, and you can see it looks a little lumpier. I actually printed this picture for Peter, but I didn't show the picture much more than just zooming in on the screen after I captured it. Now, I've disconnected this thing. Now I'm just running this up into here. And now I want to measure the total harmonic distortion with this machine up here. I could also do it with the bottom one too, but the really thing I want to show is right here as I'm zooming into this. When this distorts, it doesn't clip the top and the bottom up. It's like it's squeezing it down. It gets bulgier and looks like it's been like compressed. And what you're going to get from that is a fundamental frequency of 1 kilohertz, and then a 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, 6 kilohertz, 7 kilohertz, every multiple of 1 kilohertz. But the high frequency ones are not very large. And so what you're getting is distortion that's more in the lower audio band than if you had a transistor amplifier where you clip the top of it off, the second harmonic is gone, the fourth is gone, you get just odd multiples of the 1 kilohertz. And usually these higher frequency components are higher, and that's what's going to give you a real high-pitched sound when you clip it. And that's because it turns it into a square wave. And if you've had like 202, a square wave has only odd harmonic content. And some of the pedals actually do that intentionally. So here I grabbed that thing off the dynamic analyzer, and then you can print that. The harmonic distortion here was about 14%. It is just total harmonic distortion, just the waveform itself. Let me turn this thing on and just play some music with it a little bit here.
I want to hear the children sing. All I hear is the sound of rain falling on the ground. I sit and watch as tears go down.
Off in the middle of it just ruins my thought process.
Is the scope looking at the voltage across the speaker? Or
yeah.
The output? Okay.
Yeah, just
looking at the output of the CD player?
No, actually, I'm looking at the output of the amplifier.
Okay.
Yeah. I'm just looking at one channel. They put 2 channels on there. It was a little crowded, so.
Okay.
Any questions about the amp at all?
Was the CD player up all the way?
No.
Okay.
This again has a gain of up to 21 or 22. But as you increase the input of this, it will eventually go to that 17 volts and then distort. But as it distorts, it gives you the even multiples plus the odd. That's going to give you a fuller sound actually, and that's what people like about tubes versus transistor amplifiers. And you really can't create that easily with a transistor circuit.
So I'm just wondering about the volume. Was that like 75% full volume or what?
Well, I don't remember where I said it,
okay.
but yeah, this was the volume. Real well, you can do it here. You can do it here. So I had it set in the middle, so it's probably like a gain maybe a 13 or so, if it's not a log pot. And then this was just cranked up where it was. So, but yeah, you can go when it starts to distort. What you're doing is hitting that 17 volt limit, and that's what this can put out maximum. So, but the power does vary with load. And you can tweak it a little bit to get more power out of it. And I was hoping to do a forum on that this semester, but we'll see how it goes this semester. But given this design, if I remember right, I think I got the maximum power at about 6 ohms out. But a speaker would have an impedance that goes up, like from 8 ohms to 16, back down to 8, and then goes up again. So there's a range between 8 and 16 that you're getting with the speaker, so you're getting varying amounts of power. But if this is tweaked for 6 ohms, you're never going to see the 6 ohms, so you get a little bit less than the 8 watts that's capable of. So that has to do with how they pick the transformers, or really what they want dealing with. You got to rebias the tubes to get the maximum swing out. But, it's a nice, interesting topic. You try to do it almost every amp. But I could do it as a separate forum if I could too. So. Before I forget, there's the other thing we finished up over spring breaks. Scott finished building the power supply for this, and so it's all self-contained now. I just have a wall wart with an AC signal coming in the side here. So let me plug this in. It didn't come with an on-off switch, and we already got the thing drilled, so I'm going to leave it alone like that. So I'm going to plug this in, and it's kind of set where it was where I did it last time. And then when we bought the proto boards with our ASMSU money, they sent me a free amplified speaker, which I was going to throw in the trash can, but I didn't have room to carry another tube amp here and set that up, so we still got the synthesizer, but now it's a self-contained box. You can put a nice amp on here too, and then, it isn't too bad for a cheap little speaker, and got the little, so we'll have to play, but I think we're trying to set up some gadget time where you can start to play with this maybe, or other things, and learn to make music with these things instead of just noise like I am. But it's been fun. Scott did a great job of assembling this thing. It's incredible. The amount of work on this thing is unbelievable. So we'll hopefully do some more with this. But anyhow, but that's available too if you want to play with it. I think we'll try to set up some gadget time now, and then And then there's a couple theremins that were completed, and I'm hoping that we'll then bring those in lab too and let you play with some theremins. So.
Thanks, Wierzba.